I'll start recording the call, video, and let's share the screen. Okay. So today's talk is on word vectors. So to give a quick gist of what the talk is about today, we have a branch of machine learning and deep learning where we try to understand text. So when you're writing messages in Facebook, it recommends emojis. That's a deep learning system, most likely. And when you start typing text and Google fills in text for you beforehand, that is also a deep learning system. When you're speaking with Alexa or Google Home or other such systems, that's also a deep learning system. If you're using Google Translate, that again, a deep learning system. There's a sort of two groups. One is called CNNs, the other is called RNNs. We'll discuss that another time. So one of the key issues with text is how do we get mathematical algorithms to understand text, to deal with it. In the past, there used to be these taxonomies like WordNet, where if you gave it a word like excellent, then you could find synonyms which were written there already, like great, expert, brilliant, and so on. But it won't have something like ninja, where you would like to say, I'm a deep learning ninja. Those kind of things don't exist. It has its limitations. And the other thing is that the way we have been using words and vocabulary, essentially, we had no, the way it was being encoded, each word, there was no understanding that, let's say, orange and apple are very similar things, or king and queen are members of royalty with opposite gender. It was just a word. So that was later converted into vectors, where each word would be represented by, let's say, 300 real numbers, hopefully normalized between 0 and 1, in a way that the vector of numbers representing orange and the vector of numbers representing apple are fairly similar. So this was done in one way, and that procedure we'll discuss called word2vec. And we found out that this is very similar to the idea of principal components. So cloud vectors uses to some extent the same approach of singular value decomposition to create these vectors. Those are the two popular methods of taking words and putting them into vectors. That's what our focus will be today. Let's dive in. So this is how things used to be. If we had a vocabulary of, let's say, 10,000 words, then we would have a vector that is 10,000 long, and each word will have all zeros in that vector, but at one position, it'll be a 1. This is called one hot encoding or one hot representation, where you have a whole vector filled with zeros. Only one of them is 1 at a particular position, and each position represents one word. So let's say our vocabulary is 10,000. We have a vector 10,000 long, and for the word man, let's say we turn the 5,391st position to be 1. The vector is all 0 except there is a 1 at the 5,391 position. Second case is we have the word woman. And there the word 9,853, that is the row which is termed as 1. So you may notice they're sort of similar ideas, man and woman. They're talking about two genders of humans. But their positions of 5391 and 9853 have no correlation whatsoever. Probably they were just sorted and given those numbers. Similarly, for king, we have a vector of zeros at 4,914th position. So 1. Same goes with queen. So both these numbers 4914 and 7157 have no correlation with each other. Same with apple and orange. 456, 6257. So that's the thing which was missing in the older system. Is they were just encoded based on, let's say, their sorted position in the vocabulary. And that number where we had a 1 for a particular word had no representation of its meaning. So let's say we had a task where we said, I want a glass of orange, dash, we want to fill that up. And let's say we build a model that learns that when you say something like, I want a glass of orange, the next word should be choose. So let's say this has learned that, and now we change the sentence, and we have, I want a glass of apple, and then blank. Now, even though the model would have learned that after orange we should have choose, given the current representation after apple, the model won't know that it should have choose, because it doesn't know that apple and orange both are fruits that can be squeezed to provide juice. That was the weakness of the system. Now, let's see how we could have vectors that encode some sort of a meaning. So let's say we have the same 6 words: man, woman, king, queen, apple, orange. Let's say we have a vector of 300 real numbers. So here it's ranging from -1 to 1. And we were representing concepts like the first row is talking about gender. Let's say we assign man a gender of -1, so woman would be 1. King is a man, so it would get close to -1. Queen is a woman, it would get close to +1. Apple and orange have no concept of human genders, so they're close to 0. Similarly, we have the concept of royalty. So there we have man and woman are not royal. King and queen are both royal. So their values are close to 1. Apple and orange, not royal, so the values are close to 0. Let's look at age. So man and woman don't represent much about age. The values are close to 0. King and queen. To be a king or queen, you sort of generally reach a certain age. So this represents some value there. Apple and orange doesn't have the concept of age, so it's close to 0. Similarly, if we have a row for food, for man and woman, the values are close to 0. For king and queen, close to 0. For apple and orange, close to 1. So now you can see that each of these 6 words can be represented as a vector of real numbers, where each row of that vector represents some sort of a concept that applies to this word. That's the key idea. So let's see what this vector looks like. Let's say we took vectors of many words, and 300 is normally a preferred dimension. You can change that if you like. Let's say the vectors are 300 long. Now there's an algorithm called TSNE that can reduce the 300 dimensional vector to 2D for word vectors, where they still sort of retain some level of reasoning. So if you see man and woman, these vectors are close to each other. King and queen, again the vectors are close to each other. And king, queen, man, and woman, because they're sort of talking about similar ideas, humans of 2 genders, they're somewhat close to each other. On the right hand side, we have cat, dog, and fish. These are all beings from the animal kingdom. They're close together. And if you see, the upper half is all living beings, humans and animals. Bottom left, 1, 2, 3, 4, it's a counts. And bottom right, grape, apple, oranges. These are fruits. So essentially, vectors which have similar concepts, words which have similar concepts, their vectors will have similar values. That's one of the key ideas. And those values represent some sort of a concept behind it, like gender, royalty, food, age, and so on. So these things are called embeddings because if you think in terms of a 300-dimensional space, then each word, when converted into a vector of 300 numbers, is a point in the 300-dimensional space. So each word is embedded in the 3-dimensional space as one point. That's why these are called embeddings. So let's look at a case where these embeddings are helpful. So these block diagrams are what is called a recurrent neural network. We'll go through them in another class. So here, our task is to do entity recognition. Anytime if you put words in a search engine, it tries to look for entities. Let's say you put Italian pizza in New York. Then the search engine would like to know that New York is a place, and those two words go together. An Italian pizza, where Italian is a cuisine, pizza is a kind of food. So understanding those entities comes under entity detection recognition system. So that's something that we want to do in many text-related tasks. So here, if we want to understand that Sally Johnson are two words and they represent a human. Let's say we learn that. And we're able to learn that because Sally Johnson is an orange farmer. So because farmer represents a human, Sally Johnson is not some corporation, or it's a name of a human. So let's say a model has learned that. And now we want the model to predict on second sentence, Robert Lim is an apple farmer. Now the word orange has been replaced by apple. So before, we used to have one or two encodings, where let's say orange might have been the 3000th row, which had a 1 and everything else was 0, and apple being higher, let's say it was 253, which was a 1 and everything else was 0. So there's no concept of meaning before, but now the word orange is represented by a vector of 300 numbers, and the word apple is also represented by a vector of 300 numbers, which is very similar in value to the vector of real numbers in orange. So that is sort of the key value here. So now that the model has nearly the same vector, it can use whatever it has learned to know that Robert Lim is an entity and is a name of a human.